The University of Minnesota NASA RASC-AL team presents Project Sisyphus, in accordance with all requirements of NASA RASC-AL 2020's Theme 3 Short Surface Stay Mars mission. Project Overview. Project Sisyphus was designed to prioritize crew safety and mission integrity, maximize the value of a short-stay Mars mission, and to utilize technology that would be available and well-developed by the time the mission commences. The path to Mars will be paved by predecessor missions. Starting in 2025, a small crew will ascend to LEO to study the effects of artificial gravity on the human body. Between 2031 and 2035, more than 20 launches will be required to assemble the MTV in a Lunar Distance Earth Orbit, or LDEO. In 2033, the crew will ascend to join the MTV in an Orion capsule, finishing its construction, and shortly thereafter departing our orbit, on an opposition-class transfer to Mars. For 30 days, the MTV will orbit the red planet, during which time the surface crew will perform science operations on the surface, and thereafter return to the MTV, sterilized samples in hand, for a nearly year-long return trip home. Nearing arrival home, the crew will board the Orion capsule, undock from the MTV, and enter Earth's atmosphere directly from interplanetary space. The MTV will be remotely piloted, propulsively capturing around Earth's orbit, returning to LDEO, primed for future missions.
Costs during transit come in the form of delta V, the time of flight to Mars, and the total mission duration. The delta V must be minimized to the point that the amount of fuel carried by the MTV is actually feasible. At the same time, we do not want an excessively large time of flight, as this increases the amount of time the astronauts can experience physical degradation before setting foot on the Martian surface. Additionally, a large time of flight increases the time between the launch of the landers and surface equipment and their usage at Mars, which inherently increases mission risk. To address these concerns, Project Sisyphus employs an opposition-class mission enabled by a Venus flyby on the return trajectory, reducing the stay in Martian orbit to meet the window of the surface mission. To further decrease fuel cost of our trans-Martian injection burn, which is our most costly burn due to the MTV's initial mass, a lunar distance Earth orbit is also employed. The table shown here displays all the maneuvers executed by the MTV along with their associated trajectories and durations. A 2033 transfer window was chosen as it holds the lowest energy trajectories to Mars from opportunities in the late 2020s to the mid-2030s. The second lowest energy transfer in this window also holds the lowest time of flight, making it the ideal departure date to satisfy our requirements. An opposition-class mission with this departure trajectory has a total mission duration of about 563 days, a massive improvement upon a conjunction-class mission, which usually has a total mission duration of about 1,000 days. Additionally, a similar opposition trajectory is also possible in 2035, allowing the use of 2035 as a backup launch date in case of schedule slip.
Space operations.
Selection of launch vehicles was dependent on 4 factors: cost, fairing size, frequency of launches, and lift capacity. It was desired to have all launches done within the span of a year and a half. This led to using New Glenn to carry the MTV sections for its large fairing volume but low lift capacity, Falcon Heavy for all fuel due to its decently high lift capacity and high frequency of launches, and SLS to carry all landers and humans to the assembled MTV. SLS will be used for its high lift capacity.
Maintaining crew mental health, physical health, and productivity will be a challenge during transit. The crew will spend most of their time aboard the Martian Transfer Vehicle, or MTV, conducting research and preparing for the surface mission. In addition to adhering to all habitability and fit-for-duty standards per NASA Standard 3001, the MTV will be equipped with a centrifugal artificial gravity system to keep astronauts strong, private personal spaces to keep astronauts sane, and an expansive volume with high visibility to facilitate communication. The human-machine interfaces aboard the MTV will necessarily be adaptable and dynamic. Being prepared for emergent issues and operational changes will be instrumental to mission success. To this end, the MTV will feature a makerspace where the crew will use 3D printers, input-output devices, controllers, and more to design and manufacture tools as they are needed. The crew will also be able to interact with the MTV using their personal devices, and this data will be tracked in order to observe macro-level behavior. Highly customizable and interactive controls will make the crew comfortable and allow them to respond to rapidly changing needs. Astronauts will have a year and a half on the MTV to conduct human research, carry out technology demonstrations, and record observations of space during transit and orbit. Medical research will be critical for both this crew and all future missions. Tear collection, urine analysis, ultrasound, retinal imaging, and X-ray imaging are all non-invasive methods for monitoring the crew's health. Spaceflight-associated neuroocular syndrome and musculoskeletal deterioration are of particular concern because they will affect astronauts' ability to carry out tasks. CubeSats will be utilized as a cost-effective method for communicating with Earth and demonstrating innovative technologies developed by academia. Small telescopes with diameters as small as 1.5 meters will be able to take high-contrast images of exoplanets at a fraction of the cost of large telescopes. The Sisyphus mission will further multiple NASA science priorities on the surface of Mars and in orbit.
In designing a propulsion system for the MTV, a few major factors were considered: burn time for our required maneuvers, engine efficiency and reliability, overall system equivalent mass, and operational safety. 4 different configurations were considered: a pure ion electric system, a pure chemical system, a hybrid of chemical systems and ion electric systems, and nuclear thermal propulsion. We chose nuclear thermal propulsion. A cornerstone of Project Sisyphus is relying on the low-cost orbit of our commercial partners to bring as much useful equipment with us as we can. In doing so, we found that using nuclear thermal over chemical options saved us 80% in overall system mass and drastically reduced our window of assembly that we'd have to pursue. Additionally, ion electric engines were found to be relatively ineffective due to the massive size of this vehicle, and for the mass and fuel savings that they gave us just weren't very practical to implement, we believed. Additionally, the new congressional funding and plans for aggressive flight testing by 2024 or soon thereafter gave us a lot of promise that this technology, which has long been touted as a lost wonder of the world, would actually come into fruition in our time. Characteristics for our nuclear thermal engine were pulled from a recent NASA paper, which proposed a NERVA-derived, more flight-adapted design. It provides 111 kilonewtons of thrust, is rated for 10 hours of burn time, and in our design we chose 4 of these, which would be mounted at the rear of the vehicle for a few reasons. Number 1, just raw redundancy, the more the better. Additionally, the 4 engines allows for a very powerful 444 kilonewtons of thrust, which will allow us to accomplish kind of very quick, short maneuvers, increasing our overall efficiency. And they can also be burned in engine pairs, reducing wear on actuator components and allowing us to extend the overall lifetime of these engines.
NASA Standard 3001 requires that muscular strength and bone mineral density must be maintained above 80% of baseline values. This is a difficult requirement to meet for current ISS astronauts who spend 2.5 hours every day exercising but still exhibit significant deterioration. Reduction in muscular strength, loss of bone mineral density, and increased orthostatic intolerance may lead to difficulty performing their required tasks. Artificial gravity will be necessary to address this risk, but there are still many unknowns. There is no data to suggest what level of partial gravity or what duration spent in partial gravity will be sufficient to mitigate deterioration. Rodent studies suggest that there is a minimum efficient gravity level between 0 and 1 g, but this level is unknown. Furthering this research will help define the gravity effectiveness threshold, and longitudinal studies of this crew will provide much needed data.
Let's talk about the artificial gravity concept. We've got a couple of requirements that define this design. We're looking at less than 25% gravity gradient across the body, which means, for example, if there's 1 g at the feet, there has to be at least 0.75 G at the head. We're talking about the astronauts here. We're also looking at fewer than 23 revolutions per minute, and this is a disorientation limit. As above 23 RPMs, it is challenging for astronauts to adjust to that revolution rate. So we've designed a artificial gravity concept that has a radius of 7.78 meters, therefore is intermediate radius centrifuge, with 0.4 Gs at the head of the tallest astronaut at 6 feet 4 inches. This results in an acceleration of 0.533 Gs at the feet to satisfy the 25% gravity gradient. This centrifuge is spinning at 2.51 revolutions per minute. Now, a couple of notable things about this design is that it is designed to be an oblate spinner, which means that the axis of the main cylinder is the axis about which this design is symmetric. So we have coined that the IX axis. So the IY and IZ axes of inertia have the same magnitude. This should result in a very small control input to maintain attitude during transit of the MTV.
The hyperbolic excess velocity at Mars for our ballistic transfer is nearly 4 kilometers per second. In order to minimize the capture delta V, we first insert into a polar, highly eccentric 100 kilometer by 13,000 kilometer orbit. The non-human landers then undock from the MTV and re-enter over 2 orbital periods at periapse. The MTV, along with the human lander, uses the drag of the Martian atmosphere, along with 2 burns at periapsis and apoapsis, to shift to a 300 kilometer circular parking orbit. This orbit is more operationally ideal for the mission, as it allows 2 predictable launch, ascent, and rendezvous opportunities per Sol. Finally, the 3rd human lander will undock with the 2 astronauts aboard and descend into position for EDL.
Over the course of 3 days, each lander will descend from a polar orbit to Jezero Crater. The first will be Obsidian, containing the Mars Ascent Vehicle. The second, Onyx, containing our habitat, science equipment, and power infrastructure. And the third, Opal, containing the rover, construction equipment, and the crew itself. These landers will all utilize high-ad technology and subsonic retropropulsion to land within a 15-kilometer landing ellipse on the surface of Mars. Surface operations.
Jezero Crater is an ideal landing site because it's near the equator to get adequate sunlight. It will be scouted in advance by Perseverance, and it's a science hotspot. The delta deposits in the northwest region may have preserved organic molecules, making it the perfect spot to search for life. Jezero's igneous regions can also help answer questions about the crater's volcanic and fluvial time histories.
2 astronauts will descend in the Opal lander, which contains the off-Earth tracked rover. They will then travel via the lander to the Onyx lander, which contains the Buntab scientific equipment and power infrastructure. The lander crane will then be used to remove the lander fairing and unload the lander. Science experiments on the Martian surface will include launching atmospheric balloons to learn more about Martian weather and climate, and microbiology experiments where Earth-born microorganisms and a microgravity glove box will be assessed for how they react to the Martian environment. In situ science experiments will include water extraction from the Martian atmosphere, oxygen acquisition based on the MOXIE program on the Perseverance rover, an advanced plant habitat that will provide a small food source and biomass production, and 3D printing using Martian regolith. Sample collection will include short-term samples, which will be mainly used to determine whether a sampling site is of scientific interest, and then where to sample next. Long-term sample acquisition will focus on total diversity and total mass of samples. All long-term samples that head back to Earth will be sterilized before they leave the Martian surface, so all analysis on non-sterile samples will be done in the Shed Lab on Mars. Samples of interest include unweathered igneous rock, leftover water sediments, rock cores, and Martian soil. Sample analysis will involve wet chemistry reagents, a gas chromatographer, mass spectrometer, and a potassium argon laser. This surface schedule shows an example of what the astronauts' time on Mars will be like. Most of their time will be spent on sample collection and analysis.
Derived from NASA's current science mission priorities, Project Sisyphus will engage in 3 major areas of study. Number 1, the search for life. Number 2, characterizing the Martian environment. Number 3, demonstrating ISRU technologies. In order to maximize the value of time on the surface, sample collection will be diverted towards 2 main priorities: in situ science, which will allow us to look at unsterilized samples and inform collection efforts while still on the surface, and at-home science, which will allow us to further overall scientific understanding and plan for future missions. In designing a habitat for the Martian surface, several different factors were considered, primarily stowed volume, ease of deployment, and habitability of the actual space. In order to overcome these issues, we developed the Buildable Nested Deployable Temporary Habitat, or BUNT-HAB for short. The BUNT-HAB is an inflatable habitat derived from Bigelow Aerospace's inflatable technologies. It features a semi-toroidal outer body wrapped around a central hard core, which contains all of our hardware, equipment, and hard points. It features a hybrid suit port dock to reduce contaminants potentially leaking into the habitable space, and it is deployed off the lander using an athlete-derived rover. This athlete rover will step off of the lander, seat itself in an area that's been carved out by the bucket of the off-Earth tracked rover, and then be buried by the rover, providing a rigid, stiff, strong support base for the habitat once it's actually on the surface.
The Shed Lab was mainly designed out of biosafety requirements. It acts as a separate module from the BUNT-HAB and is an unpressurized area protected from the Martian environment to perform experiments. Astronauts will wear their EVA suits inside the lab, with the suits acting as biosafety suits. Experiments that include biological material from Earth, like the microbiology experiments in the plant habitat, will be conducted in pressurized science glove boxes.
Let's talk about the Off-Earth Tracked Rover, or OTTR for short. This is Project Sisyphus's design submission to fulfill the requirement that the astronauts need a pressurized rover on the surface of Mars to aid in the search for life. It comes equipped with a number of tools to do so, in addition to helping assemble the BUNT-HAB in the Shed Lab, moving radioisotope thermoelectric generators, and collecting samples. We were seeking a very robust design for this OTTR to cut down on the amount of maintenance that the astronauts were required to perform, and so we chose a tracked drive train. This was seen as very durable and resistant to failure on the terrain types that we were expecting. Additionally, we were shooting for a 30-mile-an-hour top speed, which is about 13.4 meters per second. We saw this as a good balance of both safety and speed when traveling around Jezero Crater.
A tracked rover design is unique to the Sisyphus mission. Tracks were selected over traditional wheels for their remarkably high traction, considerable maneuverability, and robustness to terrain. The OTTR is inspired by vehicles like PowerTrax's PT-8 snowplow and the Army's multi-purpose vehicle, which have a high payload capacity and can drive off-road in rugged conditions. Tracks distribute the maximum load over a greater area than wheels, allowing the OTTR to carry more than 11 tons reliably over the surface of Mars.
To increase the usability of the rover, several attachments will be used. A crane will be used to move large equipment in and out of the bed. A bucket will be used for the clearing and transportation of regolith. A drill will be used for scientific purposes, and a hammer will be used to drive in stakes for the habitat as well as to break up regolith. A ladder will provide easy access to the bed for the astronauts, and suit ports will be located in the bed.
The primary concerns for design of the surface power architecture include total mission energy, peak power demands, surface power mass, solar panel efficiency, and operation in the case of unit failure. To meet peak power and mission energy requirements, 10 kilowatt radioisotope thermoelectric generators called kilopower units are employed. These RTGs achieve their high power output through the use of high efficiency Stirling engines and can deliver more power per kilogram to the surface than a large 40 kilowatt fission power unit. To further reduce mass, 7 kilowatt ultraflex solar arrays built by Northrop Grumman are used to supplement the number of RTGs needed on the surface. It was found that a combination of 2 kilopower units and 3 ultraflex arrays were able to meet both mission energy and peak power requirements. To ensure reliability, the same VAC cables and power inverters are used for both the ultraflex arrays and kilopower units, since they're in roughly the same power range. Additionally, all power lines delivering power to or through the habitat will have input filtering and surge protection on them to ensure that the habitat's critical electrical systems remain intact. In addition to being optimized for mass, the power architecture is designed in a way that allows for completion of the mission objectives, even in the case of multiple unit failure. Alternative surface mission durations and operations are expanded upon in the table shown here. There are other alternative operating modes beyond those listed in the table, but the risk is considered too high for surface operations to still take place, so packing and LAR are undertook almost immediately. One concern not addressed in the previous power slides is how the efficiency of the ultraflex solar arrays will be maintained in the presence of charged dust particles. These charged dust particles also pose a threat to astronauts as they contain perchlorates and can stick to their suits, making their way into the habitat through the docking interface. To solve this, Project Sisyphus employs the use of an electric curtain. This device uses wire electrodes along with a multi-phase voltage source to levitate dust particles off of surfaces and carry them away with a traveling electric force wave. The device uses simple components, requires relatively low automation, and the electrodes can be easily planted in any dielectric.
A Mars sample return mission is classified as Restricted Category 5 by Planetary Protection Guidelines. There are additional requirements outlining prevention of forward and backward contamination. Our goal is to meet most of these requirements. Given the high TRL approach and short-term limit of this project, it would be very difficult to satisfy and measure some quantitative requirements like the one circled here. Given these difficulties, we aim to prevent backward and forward contamination as much as possible in this mission design. Our planetary protection plan is split into two categories: forward and backward contamination prevention. Forward contamination prevention starts with biobarriers being installed on the exterior surfaces of the MTV and landers. HEPA filters will also be installed in the pressurized habitat to prevent contaminated air leakage. Before launch from Earth, the MTV and landers will be sterilized via dry heat microbial reduction. As an added precaution, vapor hydrogen peroxide will be used to sterilize the inside of the habitat before astronauts leave the Martian surface to ensure that air leakage won't contain Earth contaminants when they leave. Backward contamination prevention starts with containing Martian samples with in situ containers for analysis in the shed lab. Before ascent from Mars, all samples will be sterilized and contained via brazing. The ascent vehicle which contains the samples will likely be free of Martian biological contaminants due to solar wind and microgravity. Finally, an Earth entry vehicle will be used to capture the ascent vehicle before it enters Earth's biosphere, ensuring we break the chain of contact with Martian material.
The main goal of the ascent vehicle was to limit system complexity while safely getting the astronauts to the Martian transfer vehicle. To limit system complexity, all of the ascent vehicle will fit within a single lander. This means that the fuel and structural mass must be below 22 tons. To limit fuel mass, a single vacuum-optimized Raptor engine in a single stage-to-orbit configuration will be used, giving a fuel mass of about 18 tons. Because science is of great importance to this mission, the structural mass was also limited. To do this, the astronauts will stand during ascent, much like the Apollo missions. This allows for sample return of about 600 kilograms.
Validation of the MAV's ability to reach the MTV's 300-kilometer parking orbit was undertaken by applying first principles to obtain an overestimate of the fuel mass necessary to reach this orbit. These results were confirmed using a launch segment simulation in Astrogator. The conservative estimate was made using a modified version of the Tsiolkovsky rocket equation that included a term for constant gravity. It was determined that assuming alignment of the gravity vector in the opposite direction of the thrust vector for the entirety of the burn time would yield an overestimate of the fuel mass required. The results of this calculation showed that our initial estimate of 18,000 kilograms of fuel mass was roughly 1,500 kilograms more fuel than was needed to reach the desired orbit, for a sample payload of 600 kilograms. Instead of increasing the sample payload, it was determined to keep the safety factor on fuel mass, ensuring that plenty of fuel would be available for orbit phasing and additional rendezvous maneuvers.
Budget and risk.
The first step in estimating the cost of Project Sisyphus was to compute the NASA budget from 2021 to 2035. This was done using the 2020 Explore budget estimates and was found to be about $84 billion. The Apollo missions were then used as a relevant historical analog and adjusted for work efficiency increases and inflation and calculated to be about $165 billion if done today. Both the development and deployment costs were then estimated using historical analogs, cost estimating relationships, and current prices The development cost was calculated to be about $94.7 billion, and the deployment cost was calculated to be about $22.7 billion. Summed up, this is about $117 billion for the mission. This number is higher than the NASA budget available, but lower than the Apollo budget, and was thus deemed reasonable. The highest driver in this budget is the integration and testing, which is necessary as this is a human mission and was calculated to be about $33.6 billion. After calculating the mission costs, it was important to break down development and deployment into a yearly budget. This was done using an optimal project budget schedule and is shown. It is important to note that several years have a cost that is equal to approximately half of NASA's yearly budget.
Failure mode and effects analysis shows the greatest mission risks will be forward and backward contamination, irreparable damage to the otter, and crew injury due to deterioration. These highest priority risks have high severity, high probability of occurrence, and low likelihood of detection. There will always be risks associated with human spaceflight. The risks associated with the Sisyphus mission are acceptable. The risk of forward contamination is extreme, but unavoidable if humans are to ever have a sustained presence on Mars.
Conclusion. Project Sisyphus is a fundamentally different Mars mission. Leveraging the low-cost orbit capability of our commercial partners, Project Sisyphus will overcome the technical hurdles in its way. Through the use of rugged, capable equipment like the Otter, the Bunt Hab, and the artificial gravity system, natural barriers to exploration will be passed by. Through the use of equipment like the Electric Curtain and the Shed Lab, our planet will be protected while we explore others. This will happen in our time. Let's do it. The University of Minnesota NASA RASC-AL team would just like to thank everyone here today. Thank the people at NIA, at NASA, the RASC-AL Steering Committee. It's been a great opportunity to work on this project, and we'd just like to thank you all for your time.